In this video, we're going to look at linear models and applications. This is a very fancy heading for word problems that we're all so fond of. So we're going to go through a lot of practice setting up equations to solve particular applications. Jason is driving on a long road trip. He currently has 10 gallons of gas in his car. Each hour that he drives, his car uses up 0.8 gallons of gas. How much gas would be in the tank after driving for 3 hours? How much gas would be left in the tank after T hours? So T represents the number of hours, and A of T is going to be our amount of gas left after T hours. So we're setting this up in function notation. So we know that Jason is starting with 10 gallons of gas, and that every hour that he drives, he's using up or decreasing the amount of gas. So decreasing is going to imply subtraction, 0.8 gallons. So we're going to subtract 0.8 for every hour that he drives. This is our equation, that last part of this problem, how much gas would be left after T hours. So this equation is going to be able to evaluate for however much time that Jason's driving, how much gas is left. They also want us to find how much gas would be in the tank after driving 3 hours. So that's finding A of 3. So 10 minus 0.8 times 3. This is 7.6. And with any application, it's highly encouraged that you interpret your answer to make sure that it's reasonable. I find that this is where we often identify we've made a mistake somewhere. So what this tells me is that after 3 hours, Jason's going to have 7.6 gallons of gas remaining. Now, determining whether an answer is reasonable is not the same as verifying that your answer is correct. If I had, say, solved this out and I got 76. So interpreting that, it would say after 3 hours of driving, Jason has 76 gallons of gas remaining. That should signal a red flag. One, we didn't have more than, we started with 10 gallons of gas and we're using up gas. So we shouldn't be more than 10 gallons. 76 gallons is a very, very large amount of gasoline. If you think about your own vehicle, most of our cars are somewhere in the range of like 12 to 20 gallons of gas. So 76, which would have happened if perhaps we had not done a negative and a decimal here. The other issue might be if we had ended up with, let's say we did 10 minus 8 times 3. So 10 minus 24. Then we end up with negative 14. That's a pretty unrealistic or unreasonable answer. So by interpreting this answer at the end, we can kind of determine, does this make sense or not? And then you can always apply any other technique to check your answer that you wanted. A chemist needs a 20% solution of alcohol. She has 10% solution on hand as well as a 35% solution on hand. How many liters of the 10% solution should she add to the 3 liters of the 35% solution to obtain the 20% solution? So this is a really common type of problem. We often refer to it as a mixture problem. But whenever we're setting up these word problems, a lot of times it helps us to sort of step away from the symbolic form of the equation and write it in terms of what they're explaining. So I know I need to take the amount of 10% solution. We're going to add that to the amount of the 35 solution or 35% solution. And this is going to give me the amount of the 20% solution. What we don't know is how much of the 10% solution we have. So we're going to call this X, but the amount of solution needs to be multiplied by the strength of that solution. So we're going to do 0.10 times X plus, we know the amount of that 35% solution is 3. Again, we're going to multiply that by its strength, so 0.35 equals the amount of the 20% solution. The amount is going to be X plus 3 because we have X liters of the 10% solution, 3 liters of the 35% solution, and the strength of this is 0.20. Now we're going to simplify this equation to solve for X. This becomes 0.10X plus 0.35 times 3 is 1.05 equals, distributing the 0.20, we get 0.20X plus 0.60. We have this linear equation, variables and constants on both sides. In a previous video, I had mentioned I like to combine or think about the variable terms first to ensure that I don't get a negative coefficient on my variable. So I'm going to start by saying, okay, I've got 0.10X and 0.20X. I know I want to subtract 0.10X from both sides. And that's going to ensure that my coefficient on X is positive. But at the same time, I'm going to move my constants. So if I'm bringing my variables to the right, that means I'm bringing my constants to the left. I can simplify. Those are going to sum to 0. Those are going to sum to 0. And now 0.105 minus 0.6 is 0.45 equals 0.1x. If I divide both sides by 0.1, x is equal to 4.5. And again, we want to interpret this answer. So x was equal to the amount of solution for our 10% solution. So our chemist needs 4.5 liters of the 10% solution to be added to the 3 liters of the 35% solution to obtain that 20% solution. Luca took 1.5 hours to fly her plane from her home airport with the wind to Helena. When she returned the next day, it took her 2 hours against the wind to go the same distance. If the wind during both trips is 15 miles per hour, what is the speed of the plane in still air? This is an example of an application involving distance equals rate times time. We're trying to find the speed of the plane in still air, so we're going to go ahead and identify that variable. I'm going to use S for speed, and actually, maybe I won't use S. The reason I'm thinking I don't want to use S is because S can sometimes look like a 5. So if I can try to make it so that I don't have any catch-ups on it, then that's easier. So I'm going to actually use R for rate. So this is going to be the speed of our plane in still air. The relationship we're going to be using is that distance is equal to rate times time. And I'm going to build a table for these values. Now, there were 2 trips that we're going to fill out this table for. With the wind and against the wind. That first sentence tells us that in 1.5 hours, or it took Luca 1.5 hours to fly from her home to Helena with the wind. So we know that the time here is 1.5 hours. Now, if she's traveling with the wind is adding to the speed of the plane in still air. So this is going to be represented by R plus 15. The next sentence says that when she returned the next day, it took her 2 hours against the wind to go the same distance. So the time is going to be 2 hours against the wind. And if she's traveling against the wind, that speed of the wind is actually taking away from the speed of the plane in still air. So it's going to be R minus 15. Now we know that distance is equal to rate times time. So the distance in each of these is going to be the rate times the time. So R plus 5 times 1.5. And I'm sorry, this should be 15. R plus 15 times 1.5. And then the distance against the wind is going to be R minus 15 times 2. We also know that both trips were the same distance. So these two expressions that we just calculated or just set up for D are going to be equal to each other. So 1.5 times R plus 15 is equal to 2 times R minus 15. And I just put that coefficient out front just for more familiarity. We're going to go ahead and distribute on both sides. We get 1.5 R plus 22.5, excuse me. Equals 2R minus 30. I'm going to first move or make a decision to move my variables. So I've got 1.5R and 2R, so I'm going to subtract 1.5R from both sides. And I'm going to add 30 to both sides. My 1.5R on the left-hand side cancels or sums to 0. The 30s sum to 0 on the right-hand side. And we're left with 52.5 is equal to 0.5R. Divide both sides by 0.5. R is equal to 105. Looking back to how we identified R is the speed of the plane. So to interpret this, we would say the speed of the plane in still air is 105 miles per hour. When an odd integer is added to 3 times the next consecutive odd integer, the sum is 114. Find the value of the greater integer. So we want to set up some expression for the first odd integer. We don't know its value, but we can set up an odd integer with the expression of 2n plus 1. So it doesn't matter what n is, we're always going to be adding 1 to it, making it an odd integer. We're never going to end up with 0 or an even number when we add that 1 to 2n. If this is our first odd integer, the next odd integer is going to be 2n plus 3. So we're just adding another 2 to get to the next odd integer. We're told that when the first odd integer is added to 3 times the next odd integer, the sum is 114. So we know that the first odd number plus 3 times the next odd number is equal to 114. And now we can substitute in those variable expressions. So the first odd integer was expressed with 2n plus 1. The second odd integer was expressed 2n plus 3 equals 114. We want to simplify the left-hand side. We're going to do that by starting with distribution. So 2n plus 1 plus 6n plus 9 equals 114. Continuing to simplify the left-hand side, combining like terms, 2n plus 6n is 8n plus 10 equals 114. Subtracting 10 from both sides, 8n is equal to 104. Since I'm running out of space, I can't draw this next step below this, but I'm going to divide both sides by 8 to get n by itself. And 104 divided by 8 gives me 13. So n is 13. Again, you always want to make sure you're interpreting your answer and thinking about what the question's asking us to find. The question didn't ask us to solve for n, doesn't even define n. The question's asking to find the value of the greater integer. The greater integer is given by that next odd integer. So 2 times n, which we solved to be 13, plus 3. Simplifying 2 times 13 plus 3, this is 29. Dan has invested some money in 2 ways. Part of the money into a 2% interest and 3 times as much money into a 2.25% interest account. Find the amount invested at each rate if the total amount of annual income from interest is $2,187.50. So our total interest is equal to the interest from the 2% account plus the interest from the 2.25% account to give us our total interest. So again, what I'm illustrating here is setting up an equation, but not symbolically. Okay, the only thing symbolically that I've added are the operations and that equal sign. Now that I have an idea of how to set this up, I can work with each component individually. I know my total interest is $2,187.50. I don't know how much is going into that 2% account, so we're going to call that X, but the interest earned is going to be 2% of that, so 0.02 times X. I don't know how much is being invested in the 2.25%, but I know it's 3 times the amount that I've invested in the 2% account. So this is going to be 3x, and that rate is 0.0225. We're going to simplify 0.02x plus 0.0225 times 3 is 0.0675x equals 2,187.50. Combining like terms on the left, we have 0.0875x equals 2,187.50. And we're going to divide both sides by 0.0875. X is equal to 25,000. Again, going back to that problem, making sure that we can interpret this correctly. We want to know how much was invested at each of those interest rates. So X is the amount that he invested into that 2% account. So Dan invested $25,000 in the 2% account. And 3 times that into the 2.25%. So 3 times 25,000 is 75,000 into the 2.25% account. So these were some probably very familiar examples to you. Hopefully you felt like this was a good review. But what we're going to do is kind of lead this into what we call an optimization problem. This is a really common problem that we see in calculus. An optimization problem involves trying to find the maximum or the minimum in a scenario given certain constraints. So we're going to set this up. We're going to be using technology to evaluate these problems. When you get into your calculus class, you'll learn techniques algebraically for how to solve these. So the directions tell us to set up and solve with our calculator the following problems, round our answers to the nearest hundredth as necessary, and make sure again that we interpret our answer. That interpretation, whether it's included in the directions or not, always a good practice, just to, again, ensure that your answer seems reasonable. Of all rectangles of area 100, which of them has a minimum perimeter? So what we're trying to do is minimize the perimeter. Perimeter is equal to 2L plus 2W in terms of a rectangle. We are given that the area is equal to 100. That's a fixed. And we know area is equal to length times width. So this given information, this is often called our constraint. If our area is equal to 100, which is equal to length times width, this tells us that the length is equal to 100 divided by W. So I just rearranged that equation. And I'm going to plug that back into my perimeter formula. So perimeter is equal to 2 times L. But instead of L, I'm going to write this as 100 over W plus 2W. I'm going to go ahead and simplify this. This is 200 divided by W plus 2W. And this gives us the equation for our perimeter with this constraint that the area has to be 100 factored in. We're going to graph this on Desmos to see what this looks like. Again, we're trying to minimize perimeter. All right, so in Desmos, we're going to type in that perimeter equation. Now we are going to substitute for variables y and x in Desmos. So perimeter is going to be our y. Y equals 200 divided by, instead of W, we're going to use X. And that's simply because Desmos doesn't have those variables P and W. Plus 2X. Now this did not show up very well, so I'm going to zoom out until I start seeing that graph. Okay, here it is. So there's the graph, and we can very clearly see that we've got that minimum. And if we click on Desmos or click on the graph, it's going to tell us what that minimum is. So the minimum occurs at the ordered pair 1040. So if that minimum occurs at 1040, we want to make sure we interpret that ordered pair correctly. That independent variable, that first term, is actually our variable W. And the output, that dependent variable, is P, is our perimeter. So the rectangle that has an area of 100, that has a minimum perimeter, has dimensions. Width is equal to 10, which means that the length, if I do 100 divided by 10, that's 10. And I used the relationship that we solved for L equals 100 divided by W from that area constraint. This rectangle is going to have the smallest perimeter with an area of 100. Find the point P on the curve y equals x squared that is closest to the point 18, 0. What is the distance between this point and point P? So let's think about what this looks like visually. Y equals x squared, and I'm just going to sketch this. Y equals x squared is that parabola that opens up starting at with the vertex at 0, 0. 18, 0 is some point over here along the x-axis. So what we're trying to figure out is what point P on that curve has a distance between those 2 points that is the smallest. So we're trying to find the closest point, so we're trying to minimize distance. Since we're trying to minimize distance, that's using the distance formula. So we're plotting between 2 points, 18, 0, and our point P, we're just going to call this xy. Our distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. And this formula might look a little different. We can change the order of those x's and y's because they're being added. So that doesn't make any difference. So your version might look slightly different, and that's okay. Thinking about those 2 points, 18, 0 and xy, this is going to be 18 minus x squared plus 0 minus y squared. I'm going to leave that 18 square root of 18 minus x squared just the way it is. But I'm going to simplify the next one because 0 minus y is negative y. And if I square that, I just end up with y squared. But this is where our constraint comes in. We know that y is equal to x squared. This is our constraint. So I'm going to use this to substitute into my distance formula for that y. Instead of y, we have x squared being squared. And all of this is under the square root. So simplifying this just a little bit further to make it easier to type into Desmos, distance is equal to the square root of 18 minus x quantity squared plus x to the 4th. All right, so back to Desmos, we're going to clear out that previous equation. We're going to do distance equals, so that's going to be our y. This y equals the square root of 18 minus x squared. Make sure you scroll out of that exponent, but stay under the radical minus x to the 4th. Minus x to the 4th. Oh, I'm sorry, it should be plus x to the 4th. Wondering why that graph looked so funny. So we can see this graph and a couple things that we want to pay attention to. We are talking about distance, so distance should always be positive. We see that that's the case here. But our x values, I do want to point out that in this particular situation, x could be negative because we're just talking about an ordered pair along that curve y equals x squared. So if we look at this, we click on there, we find our minimum point. You'll notice it also did give us our y-intercept, but that's not relevant for this particular example, but just a feature of Desmos. That minimum is going to be the ordered pair to 16.492. So if we think about what this represents, this ordered pair represents, the x coordinate is in fact x, but that y coordinate is our distance. In the question, they want us to not only find the distance, that minimum distance, but also to find the point P. So point P is going to be 2, and then the y value is given by that equation y equals x squared, so that's going to be 2, 4. And the minimum distance, or the distance between 2, 4 and 18, 0, is 16.492 units. Grady is flying a kite on 50 feet of string. The kite's vertical distance from its hand is 10 feet more than its horizontal distance from his hand. Assume that the string is being held 5 feet above the ground. Find the vertical distance of the kite from the ground. So I'm going to set up a visual for this, drawing a picture. We've got Grady. Grady's flying a kite, so we've got a kite. And we know that the string holding the kite is 50 feet. So this line is 50 feet. The vertical distance from the hand to the kite is, we're setting up a right triangle here. That length there is 10 more than its horizontal distance. So if I set up the horizontal distance, making the third leg of the triangle, we're going to call that x. That means the height is 10 plus x. Now we know that the hand, so the string is being held 5 feet above the ground. So this distance is 5 feet. What we're trying to figure out is the vertical distance of the kite from the ground. If we look at our figure, that's going to be the vertical distance from his hand to the kite plus the distance from the ground to his hand, which is going to be 10 plus x plus 5, or 15 plus x. To figure out x, we're going to go back to that right triangle and set up the Pythagorean theorem. We're going to end up with x squared plus 10 plus x squared equals 50 squared. 10 plus x squared, I'm going to write that binomial out twice because it helps me visualize the foiling, and 50 squared is 2,500. Boiling out 10 plus x times 10 plus x, this is 100 plus 20x plus x squared equals 2,500. Because we're looking at a quadratic, we see those x squared terms. When we simplify this equation, we want to set it equal to 0. So I'm going to do all of that in one time. If you're not comfortable with combining those steps, just take it a few steps at a time. So this is going to be 2x squared plus 20x. And then I'm going to subtract that 2,500. And this becomes 2,400. Negative 2,400. equals 0. Now, I don't like dealing with this large of numbers. I do see a GCF of 2, so I'm going to divide both sides of this equation by 2, because 0 divided by 2 is still 0. So now I've got x squared plus 10x minus 1200 equals 0, and these numbers are a little bit more manageable. I'm going to try to factor this. So I'm thinking of factors of 1200 that sum to 10. And what I'm really thinking about are factors of 12 that are going to sum to 1. So let's think about 3 and 4, or in this case, 30 and 40. 30 times 40 is 1200. If I were to combine these with the correct signs, I can get positive 10x. So I want one of them to be positive, one of them to be negative because of that negative 1200. But I want the sum to be a positive 10x. So I know my 40 is going to be the positive value and my 30 is going to be the negative value. Zero product property tells me that I'm going to set both of these factors equal to 0. So we get x is equal to 30 or x is equal to negative 40. But because x is a distance, that negative 40 solution can be eliminated altogether. So we've solved for x, but again, going back to the problem, identifying what we're actually being asked to find so we can interpret our answer. We're trying to find the vertical distance of the kite from the ground. So that's the 10 plus x plus 5 expression. If I plug in 30 for x, we get that the kite is 45 feet from the ground. I apologize for cash barking. A rectangle is constructed with its base along the x-axis and two of its vertices on the parabola y equals 16 minus x squared. What are the dimensions of the rectangle that has a maximum area? What is that area? So similar to this problem above, setting up a picture of what they're describing, I think is helpful. So we know we've got a rectangle with its base along the x-axis, and two of its vertices are on the parabola y equals 16 minus x squared. So let's just think about that parabola y equals 16 minus x squared. That's going to be a parabola that opens down with a y-intercept of 16 and x-intercepts at 4 and negative 4. The rectangle is inside of this parabola with vertices on the parabola and its base along the x-axis. Now, whether you start dissecting this picture a little bit further or start setting up your equation is up to you. I'm going to start setting up the equation just so that I think it will help me figure out what I need from the picture. I know that the area of a rectangle is equal to base times height. Well, the base of this rectangle is 2 times whatever this length is. So this length is going to be x. This length is also going to be x. It's just going in the other direction. So our base is going to be 2x. And the height is really the y value of this equation. So this equation y equals 16 minus x squared, this is our constraint. And what we're going to substitute in to our area equation. We're going to simplify this by distributing the 2x. We get 32x minus 2x cubed. And we're trying to maximize this area. So let's look at Desmos to find where the maximum of this occurs. All right, so our equation is 32x, y equals 32x minus 2x cubed. Now, if we look at this graph, we have a pretty traditional cubic curve, that nice S shape. But we do want to be thinking about some of the natural restrictions here. This is representing area, so we only consider area that's positive. So we don't really even need to worry about the bottom of this graph. And X is a length, so we don't really need to worry about anything to the left of the y-axis. So we're really only looking at this part of the curve right here. So we're going to find that maximum there, and our maximum occurs at the point 2.309, 49.267. That x coordinate is the x value from that rectangle, but the y value is the area. The dimensions of a rectangle are the base times the height, or base by the height. The base we know is 2x. So that's going to be 2 times that 2.309 value, or 4.618. And there aren't any units, so we don't need to add any. By the height, which is the y value, or 16 minus x squared. The height of this rectangle is 10.669 units. And then the max area is at 49.267 units squared. A can of garbanzo beans has a surface area of 371 square centimeters. Its height is 12 centimeters. What is the radius of the circular top? A can of garbanzo beans is a cylinder. The surface area of a cylinder is 2 times pi r squared plus 2 pi r times the height. Now, visually, if we think about the surface area of a cylinder, or a can, if you will, we've got the top plus the bottom. Those are going to be the same. Plus that's the outside. So if you visualize unwrapping the label from a can, it actually looks like a rectangle. And since this long side is going to wrap around the edge of our circle, the circumference, that's going to be 2 pi r, and this is our height. Area of the top is going to be pi r squared. Area of the bottom is pi r squared. So that's how we ended up with the formula of 2 times pi r squared, that's the top and the bottom, plus the area of the rectangle, base times height, 2 pi r being that base length of the rectangular label times the height. So our surface area can be modeled 2 pi r squared plus, if I plug in 12 for my height, 24 pi r. We know that the surface area is fixed at 371. The easiest way to look at these equations is to set it equal to 0. Desmos can find our zeros very quickly, so we're going to subtract 371 from both sides. We're going to go to Desmos to see that. All right, so our equation y equals 2 pi, we're going to call it x, plus 24 pi times x minus 371. Now, if we look at this graph, if I zoom out all the way, we can see that it is a quadratic. It's that parabolic shape. It's just very long and narrow. But again, that x coordinate is representing our radius in this case. We're just using x and Desmos. So what we're trying to figure out is, what could that radius be? If I look at the zeros, we've got 2 of them here, but it doesn't make sense to have a negative radius. So we're not going to look at that one. Our 0 that we're looking at is 3.749. So the radius of this cylinder, this can of garbanzo beans, is 3.749 centimeters, because our surface area was given in square centimeters.